Guys. Alright, I'll be on Chem, and when I'll be able to teach you guys this Friday, but I thought this would be perfect time for you guys to read a little bit about the spectroscopy. Remember, we went through the harmonic oscillator, applied to diatomic molecules, and we discussed the vibrational spectroscopy for diatomic molecules. And I would like you guys to review it. That's a little bit of review for the 11C. And then the topic 11D, it touch bases on the vibrational spectroscopy. Did I say diatomic twice? It should actually be polyatomic. It's a typo there. Polyatomic. Okay? So using the lecture time, go through those two. Now, in our we will have the second midterm exam. I just want you to know I dumped the practice exam for those of you who want to prepare ahead of time. I have 3 practice exams if you want to try it. I already have a solution key posted too. Alright, so the topic 11C will be covered in your midterm exam too, which we talked about it last week. So I have 3 given to you. You don't really need to do all 3 of them. But I thought, since I've been teaching for a long time, maybe those exam papers are circulating around. So therefore, why not just give you all of them, right? Okay. Because I won't be here on Friday, so I won't be able to do the office hour. I just considering maybe some of you want to see me before the homework is due. So I decided to extend that homework assignment. For those of you who already finished it, just submit. But if you need that time, it will be due on October 17th. Okay, so that will allow you to see me on Monday for any questions. Any questions on that? Yeah.
So you said the final was just over translational and vibrational? That's
The final?
midterm.
Oh, okay. The midterm will be, okay, the midterm, you mean the content? Is that what you're saying?
Yeah.
Okay, the content will be from the start of the semester, go all the way to the content for next Friday. Okay, now some of you said, what do you mean from the start of the semester, right? That is because, what do we learn at the beginning of the semester? Review for some physics, review for some math, and then we touch bases on very important component that is the foundation of quantum mechanics. And then we apply to translational motion, to vibrational motion, to rotational motion. So that foundation will carry through the whole semester. It's like your algebra, you do plus minus, divide and multiplication. Even you take a multivariable in algebra, you still need to know plus minus. So therefore, the postulate will be carried through. That's how we are doing. Okay. Yes, will be related with somewhat of the rotational motion. That's what we're going to talk about. Right? So in that regard, I told you I dumped the exam papers. The exam dates from year to year not exactly the same, so therefore be very mindful about the content of those in the exam paper. May not match exactly. Okay, so we said we're gonna talk about 3 motions: translational, vibrational, rotational. Then we will discuss hydrogen atom. Then we will discuss diatomic molecule. And then we will see if we have time, we will talk about polyatomic, but that's the progress for this class. So we talk about rotational and vibrational motion. Now we are going to talk about rotational motion. In rotational motion, when the system rotates, right? So let's say I have a system, it can rotate on a plane. That's a 2-dimensional rotation. You also can rotate in a 3-dimensional space. So we separate those. We will start with the rotation on the ring. The ring is a 2-dimensional model, or we say on the plane, they're the same. Then we will say rotation on the sphere. That's a 3-dimensional motion. Okay, and then again, the whole point we were learning this is to apply to our systems, we will discuss about the rotational spectroscopy. Okay, so talk about rotational motion, then we will review one of the angular momentum concept. You have a translational motion, you will have a linear momentum. But if the system rotates, you will have angular momentum. Now, angular momentum can use a J for, so it's a vector, right? So you have a J. We also have linear momentum. That's your linear momentum. This is your angular momentum. All right. They are linked. So if you rotation, let's say we apply to XY plane. So you have a rotation on the XY plane. Then you will have a radius. Right. So you rotate with a particular radius. So you have a mass. Okay, so you have, let's say this, let me draw this. So you have a mass of M rotate on this XY plane. The radius is R. So the system rotates along a circle on plane with a radius of R. Then rotation can be a clockwise rotation or a counterclockwise rotation, right? So if I rotate on the XY plane, this is your clockwise, this is your counterclockwise. So therefore, let's say in these cases, the system is right here. It rotates around this plane, and then we will have a particular point. You will have the linear momentum. Now, in this case, it's counterclockwise rotation. All right, I think that's your physics model. If I really want to extrapolate, I can extrapolate the radius in that direction. You guys all follow me, okay? You have a mass of M rotates on the plane with a radius of R. R is fixed. Okay, then R is a vector, so this is the radius. If I extend it just to know the direction, I see, extend it that way, and then it rotates counterclockwise. At any point, I will have the velocity or the linear momentum. Now, where's your angular momentum? The angular momentum is the cross product between your linear momentum and position. Okay, now in math, you also learn another, which is using a dot. What is that?
Dot products.
Okay, very good. All right, so in that case, can we define the direction for the angular momentum? You can use your right-hand rule, right? How you want to do it? Yeah, you start with one, go to the other one. So basically, I put my hands here, right? And I rotate toward the other one, and whatever this is, that is the direction for the third vector. And that's what it's showing here. So in this case, the angular momentum is in the z direction because it's a rotation on the plane. Angular momentum can have an x, y, z, but for this particular one, it's the total angular momentum is only the z component. But if you have rotation on three-dimensional space, then you will have angular momentum, have an x and y and z component. Are you guys all follow me, okay? For this one, the rotation on the xy plane, the total angular momentum is equal to the component in the z component. Maybe I should just write it out for you. So the angular momentum can have x, y, and z component. This is exactly the same as your linear momentum. But for rotation on the xy plane, then the magnitude of the angular momentum total is the same as your z component, because it's only in the z direction. Okay, all right. Now, if I want to really write this one out, then I can calculate the magnitude. If it's a cross product, then I know the magnitude for the one of the vector, meaning momentum. Then I know the magnitude for the position r. Then it will be assigned is the angle between those two vectors. And I think you guys already learned this. Okay, here, what is the sign between those two vectors? Angle.
90?
Huh?
90?
This is
Right.
in this specific case, rotation on the plane, then the angle is 90. Okay, now if it's a sine 90, I always gonna sine 90 equals
1. Yeah, 1.
So for the rotation on the xy plane with the fixed radius, if we started with the definition, we calculate the angle, and they were just equal to the magnitude of the beginning momentum and the Okay, now we're going to go through that because this is the part of the model we are going to take. The other thing I want to review is for rotation, we can use Cartesian coordinates, which is x, y, and z, but we also can use cylindrical or spherical coordinates, which is r, theta, and phi. Now, which set do we want to use is how easy we can make our mathematic manipulation. That's about it, because r, theta, phi can be converted to x, y, z. They are related. Okay, now just review with you guys. You have a cylindrical, this is a 2-dimension. So if it's a 2-dimension, we will have 2 variables. If it's a 2-dimension for Cartesian coordinates, you will have x, y variables. Now, in cylindrical or spherical coordinates, you will correlate it with r. R and phi. Right? Now, what is the range for the I? I is the radius. It's between 0 to infinity. Right? Now, how about the phi? It's rotation on the plane, so the phi is from 0 to 2 pi. Okay, right. Now, if we want to know the volume, then we can keep going. So the volume, a small volume in xy plane, then the d tau will be the product of dx times dy. Okay, now if you want to use spherical coordinates based on the relationship, the r, the x and the y with respect to r and phi, then that volume will become r times dr times d phi. Okay, often our student would be directly transferred, say, okay, this is dx and dy, then this will be only what? Di and d phi. That's not true. Now, how we get the correlation from here to here is your relationship between the y is r sine theta, sine phi, and the x is cosine phi. And then you can substitute in, that is the relationship. So that's just give you guys a little bit of review. All right. Now, we say for the rotational motion, we're interested not only know the positions, but we also need momentum, but we also would like to know the angular momentum. Now, how are we going to do it? In quantum mechanics, right? So we have observables. What we want to do is we're going to come up a operator, right? So if any observable in quantum mechanics, we are going to generate a corresponding operator. And then we can operate onto the wave function. If we obtain the eigenvalue, then that is your measurements. Or we can get the mean values, we can get an average value or expectation value. So therefore, the important part is if we want to know the observable of angular momentum, then what we need to do is we need to generate the angular momentum operator. But that's not what the book wants you to do. The book wants you to confuse us a little bit. Right? What the notation they use for the, what did they use?
L.
Yeah, they want to use L. The same idea. So this just refers to the operator for the angular momentum is the lowercase l. Okay. Now how are we going to generate the operator, guys? How do we generate operators? We were given two. We were given the position operator, which is just a multiplication of that position variables. And we were given with the linear momentum operator, which is a constant times the derivative with respect to the position. Then you're going to utilize these two, plus the relationship you learned from physics between different observables. Okay, and that's what we're going to do. So in physics, you know the angular momentum and the linear momentum position, they are linked. So I'm not going to go through for all of them. So let's say the angular momentum can have the, the z component, x component, or the y component. Then you have correspondingly, you have operator for that component. Okay, now we can, through the physics, we know the component in one of the axes is the position times the linear momentum. For instance, if you want to know the angular momentum in the z, that's the product of the value of x times the linear momentum in y minus y times the linear momentum in x. And then you do the same for the other component as well. Okay, so this is the relationship. Now how are we going to generate the operator? Then you just put the corresponding component in the operation as well. So this is your relationship you learned from physics. Now if I want to generate an operator, for that one, I take this relationship and then I'll have this one my operator, right? And multiply by the operator for the linear momentum, then this will be y operator, and then the px operator. Okay, all right. Now what we need to do is plug it in, right? Because do we know the operator for the x position? That would be the variable of x multiply. Very good. Now do we know? Oh, I think at this moment we can memorize it by heart, isn't it? Now you have x, y, z components, so we should use what? Partial derivative. Okay. Any question on that? So this is your x multiplication operation. This is your linear momentum. Now let's keep going. The y will be the same. All right, and then what do you have in here?
Partial x.
Okay. All right. Now we can take the h bar of I constant out. Okay, now as indicated on the slide, I can go through with you guys. So that is your operator for the z component of the angular momentum, and correspondingly, you can generate the operator for the angular momentum in x and y. Okay. the z component. For the z component, we can convert this whole thing using the spherical coordinates. If we use the spherical coordinates, it comes up in a much simpler expression just related with the okay, so how do you do it? You just plug it in, x with respect to r and phi, and then y with respect to r and so r is r sine phi, x is r cosine phi. Plug it into your expression and you do manipulation. So therefore, you can write your operator in terms of the Cartesian coordinates or in terms of the spherical coordinates. You guys all follow me okay on this? It's really nothing fancy. Okay, so we generate down. Okay, now we can measure the angular momentum in x and y and z, as well as the total angular momentum value. Remember we learned from Heisenberg uncertainty principle is can we determine two observables simultaneously within an arbitrary, resolution? Can we do it? Now, right now, we have the total L, x component, y, and z. How do we evaluate that? Then one thing we evaluate that is to calculate the commutator. The commutator between two observables, right guys? Do you remember the commutator idea? So I have observable 1, observable 2, right? Should I put an operator right here with a square bracket? You calculate, this is what we call a commutator. Let me write out. Alright, so you have one observable, observable 2 to really evaluate the effect of the sequence of operation, vice versa. Okay, now we said if they commute, so this is a commutator. If we say those two observables they commute, this equals
0.
If they commute, then the commutator equals 0. Okay. If they are 0, what does that tell you?
You can determine both at the same time.
Can they be simultaneously determined?
Yes.
Okay, if they are non-zero, they cannot be according to Heisenberg uncertainty principle. Okay, very good. So you guys can go home and practice it. Then we can evaluate the xy component of angular momentum and y and z and z and x. What value do we have? It's a non-zero value. So it's a non-zero value. What does that tell you?
They do not.
They cannot be simultaneously determined with an arbitrary precision. You guys agree with me? Okay, you can determine one of them. All right, but what we can evaluate is this guy, and then have a Q here. That is 0. Q just refers to the coordinates. The Q can be x, y, and z. So therefore, if you evaluate the two observable, which is the total angular momentum, plus one of the component, that will give you 0 value. So what does that mean? That means you can precisely determine the total angular momentum and one of the component simultaneously. I guess follow me, okay? Alrighty. Okay. Alright. So often we are interested in learning the momentum of the total plus the z component. That's traditionally one. Of course, you can do the x and y, but those two can be measured. Alrighty, and then we can also generate the operator for the square of the magnitude. Yeah, it's the same idea as you wish. Okay, and the idea is the same. You know the relationship from the physics. You plug it in the operator, and you use the position and linear momentum relationship. Okay, so this is all review at this moment. Alrighty, for each of the motion, we will talk about it. The first thing we want to discuss is the physical model. Like, what is the physical model? Now, let us give a minute. What is the physical model for a particle in the box for translational motion? Anyone? We talk about translational motion. We use a particle in the box in one dimension as a model, and we talk about harmonic oscillator as our physical model. Okay, one of you review with me. What is the particle in the box model?
A conjugated pi system?
Huh?
A conjugated pi system?
Oh, yeah, that's an application. Just say in general statement, what is the physical model for particle in the box?
Free particle in a box, allowed free to move, can't escape the box because they have infinite potential on either side.
Okay. Yeah. Yeah, so you have a particle with a mass of m. All right. It is motion in one dimension with a box length 0 to L or L sub 1 if we're talking one dimension. And it's a free particle, which means the potential energy inside the box is 0. But at the limits boundary of the box, the potential energy is
Infinity.
infinity. That is our physical model. Based on the physical model, we can generate our variables for the wave function for that particle. We also generate our Hamiltonian operator that takes us from solving for the Schrodinger equation, so on and so forth. How about let's say for harmonic oscillator?
Potential L.
Okay, yes. I just want to have a descriptive discussion. So last time somebody raised their hand and couldn't get to the board to answer the question. I think it's you, right? Yeah, now I give you the opportunity.
Oh, I don't go right on it.
Oh, okay.
Yeah.
No, they're not calling name. Okay, let's see who I remember. Okay, I have a list right here. Okay, let's see. Okay, let's see. Do we have Nick? Okay. What do you think? Actually, I don't have another name. but I remember because when I hand out the paper, right? I met with you guys, so therefore I remember. Okay, so what about vibrational motion? Vibrational motion, what we have is you have a mass of m attached to a spring, right? The spring attached to the wall, and then the subjective to restoring force. The force is satisfying Dirac law. Force equals to the negative kx, right? And that is our physical model. Now under that model, we will have parabolic potential well. But we started with the descriptive. Yeah. Sorry, Nick, I took your opportunity. Yeah. All right, so now let's take a look at our rotation on the ring. So it's perfect because I give you guys an additional homework and describe those models. You don't have to turn it in, but you can work on it. Not this the upcoming assignment. Okay, so for rotation on the spring, all right. So our physical model. Let's see. All right. This is our physical model. It's a free particle. Rotates on the ring with a fixed radius. All right, it's a very short sentence, but carries a lot of information. So, the system only has one particle. Of course, we can define the mass as m, right? And then rotate. Rotates on a ring. You could also think ring is just a plane. Okay, so we'll start with a two-dimensional. We will start with a two-dimensional rotation. Plane, we use two variables. You can do x, y, y, z, z, x, whatever you would like to, but we just want to pick it x, y. So it's a two-dimensional system. Okay. Now, the other condition is with a fixed radius. All right, now let's see. So I have a particle, rotate. I can draw this circle better than this one. So I have a particle that rotates around this plane, okay, with a particular radius. I can make it as a variable radius, which means I can rotate, changing the, so I can rotate with different radius. But in this case, that's not true. Okay, so when we say fixed radius, in math, you can convert it into an equation or expression. What would that tell you? That means the R is a we set this R as a constant. When you rotate on the plane, you have an xy variable, but you can transfer it into R and phi variables. However, for this particular model, we say the R doesn't change. So R is your constant. So you reduce your variable from 2 to 1 because of the condition we are looking at it. Okay. Or mathematically, we can say the R is 0. There's no change of the radius. Either way, we cannot infer with that fixed radius. You guys follow me okay? So it's a free particle. Now, what does that mean? Free. At this moment, we're all going to jump up and say, free means what? Not free. Free means what?
That's free.
Excellent. So free means when you rotate on that plane with a fixed radius, very, very good, then the potential energy is 0. Okay. All right. So we dissect the system a bit better. Now, how are we going to do it? We're going to generate our variables for the system. We figure out the Hamiltonian operator. We plug it into the Schrodinger equation. They borrow your mass. We're solving for that second order differential equation. And then we will come up, impose a boundary condition, and then we come up with a wave function solution. I can repeat the whole thing all the time, but that's the idea of how we're going to do it. All right, now let's give it a shot. Okay, now can we construct the Hamiltonian operator? Now, first of all, let's come up with the variables. Because the Hamiltonian operator carries a variable. So you need to come up with a wave function which carries two variables. I have one particle move on the plane, so I have an xy. So therefore, my Hamiltonian operator will also have two variables. All right, now let's generate the Hamiltonian operator first. The Hamiltonian operator always have two components. Now we only have one particle, so therefore you only have one component of the kinetic energy for that particle. Of course, if I really want, it's also generically also have I'm just write out a generic expression. Applying to this particular system, we can simplify. What we can simplify?
Potentially.
This potential energy term will be 0. Okay, now how about the kinetic energy operator? So kinetic energy operator has two components. One is in the x, the other one in the y. So therefore, is that too easy, guys? Is that all good? We can mathematically, we can carry with the Cartesian coordinates, but it's much easier if we convert it to spherical coordinates, and I'm going to show you. Okay, so then we can convert it to the spherical coordinates from this component here. That will be with respect to the radius. Right? And then I used to ask students to show me how that works. Maybe I will ask you guys to do the same too. So basically, maybe I'm not going to make it into the exam, or maybe the homework, because you can show me this is equivalent to this guy here. I'm sure you guys learned this from your math at some point. Now, how do we do that? Because y equals r sine phi, x equals r cosine phi, we can substitute and convert it there. Okay, I'm not going to go through it in lecture. So I didn't do anything fancy. It's the idea. I don't want the math to take it away. Our idea is generate the Hamiltonian operator for that system. Carry two variables. Has the kinetic energy operator, potential is 0. I can write out the kinetic energy operator in terms of x, y, Cartesian coordinates, or I can convert it into the spherical coordinates. That's not it. Now, for this particular system, we will have a fixed radius. So we impose our constraints. So we will simplify. If you guys evaluate this, what term will be managed? The r is no longer a variable for this system. Okay? What else will be managed? This will no longer exist for our system anymore because it's a constant. Our system is a constant radius. So we reduce the variable from r phi to only phi. Alright, so therefore if we rewrite here, then this will becomes now you guys see why we, instead of using the Cartesian coordinates, it is better for us to evaluate this in terms of spherical coordinates, because now the Hamiltonian operator is equal to a constant times 1 over r squared. You have a second order derivative with respect to the angle on this xy plane. Any questions on that? It's all good? Okay, all right. Now, from the physics, if you do the m times r squared, what is that? Huh? For rotational motion, the mass times the radius?
The momentum, or the angular momentum?
No. Okay, I'll write out. This is the 2 carries from the 2 right there. mr squared, I'll combine with the notation. I'm not sure if that's what you guys are using it. Is I, still, no? So you combine mr squared, it's a moment of inertia. Moment of inertia. Okay, alright, anyway, so we can substitute the mr squared into the I, alright? Let's put a comma here. Okay, that's a lot of work to generate the Hamiltonian operator. You guys all follow me okay on this? Okay, that's what we did the first step. Alright, now what I'm gonna do is we have our wave function with the corresponding variables, and we generate our Hamiltonian operator with the corresponding variables. Our Hamiltonian operator now really is converted to the spherical coordinates equals to, right now in terms of the moment of inertia, okay? And then you have a second order derivative with respect to your angle phi. All right, okay. Now we can plug in. So then our wave function, we also carry the phi variable. So we can plug into our Schrodinger equation. That will generate our energy, return our wave function on the right side. This is our Schrodinger equation, right, guys? All right, so I didn't do anything. All I did is plug it into the Schrodinger equation. Okay, now as math is saying, you can solve for it. This is a second order differential equation with respect to the variable of phi. It will have a general solution. And this is the part we skipped, you guys have to take the word for it on the math. The solution for this second order differential equation is the wave function contains, of course, it's a wave function with a variable. We use a sub m sub l. Okay, just bear with me. Take m sub l. But this is your wave function, the solution, which carries. Now, of course, you need to have a normalization constant. So this is your general solution for that differential equation. So carry the phi variable, and we have a sub of m sub l. Immediately, we have a whole series of values. Okay, so that is your m for translational motion, v for vibrational motion. Indicates this is a solution. You have to have some quantum number to refer to that various quantum state. Okay, now this is solution is an e function raised to the power of x. As that immediately boom boom out to you. This is a complex. Right, it's a complex function, wave function, multiplied by the m sub l, then times the variable phi angle. That is your solution for the wave function for this particular law. Okay, any questions on that? Now we're not done yet, right? Because this is a general solution. This is a general solution from the mass. Now how are we going to impose to our system? How do we impose to our system from a general solution to the finalized solution from the translational motion and the vibrational motion? We need to impose the boundary, right? We need to impose the boundary. Now what would be the boundary? Okay, let me ask you, if at one point, to use a different color, at one point, so our particle rotates around this xy plane with a fixed radius of r, okay? Now let's say at this point, just at this point, right? The wave function represented by the psi phi. You guys all follow me okay at this point? Right? Now, if I add one revolution, it returns to that point. That means this value will be the same at the one revolution or add a two revolution. Are you guys all following me okay? Because it's a rotation. So I started here, whatever the value is, then after rotate the whole thing and then return to that one, then that wave function will be represented by that phi angle plus one revolution. So that has to be the same, because that is the same spot. So that is our boundary conditions. Okay. Where should I write? Can you guys see that corner pretty good? Okay, now I'm going to continue there. Okay, are you guys all okay seeing right there? Okay, so now let's do. So we're going to impose our boundary conditions. Alright. Why did I write this big? Okay, alright. So the boundary condition is you add some, at some angle, then that has to be equal with adding one revolution. This is our solution for the wave function. For the sake of simplicity, I'm not going to add the normalization constant here. It really doesn't matter. Okay, let's just remove it. All right, in that case, I'll plug it in, which equals to e raised to the I m sub l pi. That equals to the, I'm running out of space, so I'm not going to write 2 into that. So this is equal to ei times m sub l times that variable. So that will equals to ei m sub l. Now this variable will be add to pi. This is our boundary condition, not just substitute with the wave function. The wave function is ei as l pi. Now here is pi plus 2 pi, so I substitute that. It's all good? Okay, can I break this into two terms? Okay, what are they? So the right side, the same thing. The right side is e raised to the power of a plus b. Then you're going to have e raised to the power of a times e raised to the power of b. You guys all follow it, okay? So this will be I m sub l pi times okay, you guys have to say yes, otherwise I'm gonna drink my coffee right now. Is that all good? It's e a plus b. Isn't that give you e to the a times b to the b?
Yeah.
Okay, alright, okay. Now what do we see? To satisfy this boundary condition, plug it into the what has to be true? So this has to be equal to, oh no, I can't finish this, huh? So this has to be equals to 1. Okay, let me say one thing. Since I'm not seeing you guys on Friday, I cannot actually already start this, huh? So, if this has to be true, I want you guys to go home and think about it. We'll impose for this value